This is the Xuankong Hanging Temple. Anchored 75 meters above a valley floor in Shanxi province, its structural geometry presents a calculation problem that challenges our understanding of pre-modern engineering. To find the physical limit of this system, we apply the shear stress formula on cantilever beams. Tau equals V times Q over I times T, where total load V equals 180 metric tons, producing localized flexual strain exceeding 14.2 megapascals on the hemlock timber. These beams do not just rest on the surface. They are driven 2.5 to 3.0 meters deep into rock mortises hand-carved into the bedrock of the cliff. The standard historical consensus suggests these complexes were built using primitive timber scaffolding pinned to the exterior cliff face. However, the math does not support it. Calculated shear limits on raw timber scaffolds demonstrate that the combined weight of the scaffold and the construction materials exceeds the pull-out strength of primitive iron pins by 340%, an imbalance that leads to immediate catastrophic structural detachment. These accepted timelines require a physical output that contradicts recorded structural mechanics. The cliff face environment introduces another severe variable: dynamic daily temperature shifts of up to 35 degrees Celsius. This thermal cycle creates a constant wedging effect, where the expanding timber and the contracting stonework in opposition. Rather than loosening the structure over time, the temperature cycle forces the internal socket anchors to lock more tightly against the stone walls. This stability is further reinforced by a calculated chemical interaction between the timber beams and the limestone bedrock. By steeping hemlock beams in tung oil, the builders achieved a precise friction coefficient of μ equals 0.68. Under a gravity load, this exact coefficient creates a self-locking mechanical joint, ensuring that the heavier the temple, the more securely it is anchored. This self-locking engineering logic suggests a level of mechanical foresight that completely bypasses the limitations of simple scaffold-based assembly. This anomaly extends to the Meteora monasteries in Greece. These structures are perched atop 600-meter conglomerate pillars, a logistical threshold historical records struggle to explain. To calculate the labor required, we use the vertical uplift transport energy formula, E equals m times g times h. Moving 100 tons of granite up 600 meters requires generating 5.88 times 10 to the 8th joules of mechanical energy, all without internal combustion or winches. 14th century labor constraints and pack mule capacity were limited by strict physiological ceilings. Producing this precise joule output at such vertical scale was an impossibility under the recorded technological parameters of the era. On Mount Fanjing, the architectural limits are grounded in the physical geology of the Red Cloud's golden summit. The foundation is the Fanjing Shan group, formed approximately 820 million years ago during the collision of the Yangtze and Cathasia blocks. The pillars are composed of Proterozoic metamorphic rift rocks, including slates, phylites, and tufaceous sandstones. This metamorphic substrate provides a compressive strength of 180 to 220 megapascals. This rock mass acts as the primary defense against aerodynamic stress. At this altitude, turbulent wind shear slams directly into these narrow, isolated spires. The site must withstand crosswinds exceeding 210 kilometers per hour. The 220 megapascal compressive capacity of the rock is the only factor preventing these wind loads from triggering a catastrophic shear failure of the summit. To understand why the rock doesn't shatter, we must evaluate the quartz sandstone against the Coulomb-Moore failure envelope for triaxial shear. Tau C equals C plus mu times sigma n minus pf. Discontinuities in quartz sandstone have zero tensile strength, creating pathways for water to migrate deep into the cliff. When water enters these joints, the pore fluid pressure, variable Pf, increases. This forces fractures apart, lowering effective stress and pushing the rock toward failure. Ancient engineers countered this by carving micro-drainage channels directly beneath the structural mortises. Structural loads actively squeeze water out through these channels, keeping the internal pore fluid pressure near zero and maintaining the shear capacity of the rock. By controlling this exact fluid dynamics equation, the builders prevented standard weathering and freeze-thaw cycles from destroying the anchors over 15 centuries. These cantilever mechanics find a biological parallel in the petiole attachment of the plant Heteromeles arbustifolia. This plant exhibits a modulus of elasticity ranging from 180 to 1,566 newtons per square millimeter across its cross-sectional area. This biological optimization of stress distribution echoes acoustic anomalies detected at the base of the Xuankang Temple. Acoustic testing has revealed 17.4 Hz sub-audible infrasound standing waves forming within the cliff cavities. These waves match the resonant frequency of the timber support beams, effectively phase-canceling localized gravitational vibrations during high wind stress. This frequency protection is critical during major seismic events, such as the magnitude 6.8 earthquake in 1700 AD. During that shock, the flexible timber joints acted as shock absorbers, warping to take the kinetic hit without breaking. The entire structure was able to decouple from the frequent 5 to 5.0 Hz resonance frequencies of the cliff face. This precise decoupling allowed the energy to dissipate through the timber flexure, preventing brittle shear fracture, and saving the temple, while structures in the valley below were destroyed. The deep rock sockets at Fanjing hold microscopic evidence that contradicts standard manual construction. Localized vitrification warps have been discovered inside these sockets, indicating that the rock was exposed to temperatures exceeding 1200 degrees Celsius during their creation. Analysis shows rock being rapidly sheared away in a nonlinear pattern, suggesting a high-velocity force applied within a confined space. This thermal and kinetic signature is beyond the physical capability of primitive bronze or iron hand chiseling. We see a structural motif of this isolation in microscale artifacts, like the Colchian gold diadems dating from 450 BC. These ornaments use microchains and articulated joints to suspend temple-like structures, utilizing the same kinetic principles of cantilever physics. These artifacts were part of a hoard of bronze lamps buried in 50 BC, hidden deep within the ground to prevent their desecration. Whether manifested in the high-velocity excavation of a mountain peak or kinetic suspension of ritual jewelry, the structural motif remains consistent, an engineering effort to isolate the sacred via physical suspension. Preserving these stable zones is intertwined with broader ecological management. The geological isolation protecting the temples is the final refugium for the endangered Guizhou golden monkey. To maintain this habitat, the Grain to Green program uses payment for ecosystem services, converting erosion-prone farmland back into native forest. The soil supporting this forest is derived from mafic ultramafic Alaskan-type plutons found throughout the sedimentary sequence. Managing these ecological refugia requires navigating the friction between global tourism and the strict physical constraints of the mountain. These spatial constraints are dictated by the hard geological boundaries of the Fanjing group's metasedimentary schist. The structural capacity of this entire interconnected system reaches its absolute geomechanical threshold right here at the peak, where human footprint and biological survival are limited by the sheer capacity of the Fanjing terrigenous turbidites fleisch structures.